Hey everyone, on this lesson we are going to introduce Google Colab. Colab is a Google platform that allows us to write and execute Python code through the browser. We are going to use Google Colab when programming in Python for two main reasons. The first of them is that it is a free platform, anyone can use it, and also that Google Colab allows us to visualize our results in a very easy and intuitive way. To create a new Google Colab notebook, it is very easy. We can just go to our Google Drive. In my case, I'm inside the folder called course, so we can just go right click, we go to more, and Google Collaboratory. This will create a new Colab notebook. So we just go right click, Google Collaboratory. As we can see, this creates a new Google Colab notebook. Here we have the name of the notebook. We can title this any name. We can just say test, right? Now the file extension, as we can see, is IPYNB. This file extension stands for the Jupyter Notebook file. Jupyter Notebook is an interactive web application used for creating and sharing computational documents for analysis using Python. Now, on a notebook, we can add code and we can also add text. For instance, we can add a text here, and let's just type, this is a text, this is a text. We can also add a text to be a heading type with hashtag. This basically means that this is going to be the title, as we can see, and here we have a code window that we can just add Python code. Remember that notebooks are implemented in Python, so we can just, for instance, print hello world, for instance. To run this code window, we can just press Ctrl Enter or just press this play key. So as we can see, after pressing the play button, we have run this command and we can see on the output hello world. We can also print, for instance, a sum of two natural numbers, like so, and here we see that the result is 8. So now we're ready to start programming in Python in this notebook. Google Colab is really very practical, and that's why we are going to use it along this course. Hey everyone, on this lesson we will introduce the dataset that we will work with along this practice. In this practice, we will work with a dataset that corresponds to abstracts of scientific articles. We have articles from 4 categories: astrophysics, computer science, mathematics, and physics. And there are a total of 1,000 samples of each category. So in total, we have 4,000 samples. Now, to work with this dataset, you need to download 2 files. The text file, here we contain the information of all of the documents, this is a list, and also the labels file. This has the information of the document labels. Again, this is also a list. Both of these files are available for downloading on the downloadable resources of this lesson. Once you have downloaded these files, you just need to run this Python script on your notebook. With this, you're going to load both of these files and both of these lists into your notebook environment. So, let's start. We have just created a new Google Colab notebook. We already explained how to create a new Google Colab notebook previously. So now let's add here a new text window. Now let's name this window to be import of libraries. And let's start by loading this dataset into our Google Colab notebook. So in your case, you need to download these 2 files that you can check and download on the downloadable documents of this lesson. You download them, and then in your Google Colab, you go to this files window here, this files icon, and now you just go to the option to upload to session storage. So with this, you can upload new files to your Google Colab notebook. So we run this, we press this, and now you just search for these files in your computer, in your system. We already download them. We have here text and labels, so let's load them, we can just double click or just open, we load the text file, we wait for the loading as we can see in here. Very well, now we already have here the text file that we needed. Now let's also load the labels file. Now again we look for this file in our system, we go labels, we double click or just click open. We wait for the loading, and as we can see now we have both of these files loaded into our notebook. Now we can already close this files window. And now to work with these files, remember that they are lists, okay? Both of them are lists. And to import a file that represents a list in Python, we can use here with the JSON model. JSON is a syntax for storing and exchanging data. So we need to import now the JSON library. We import this library in here, import JSON like this. And now let's add here a new text window. Let's just name this window initial study of the dataset. And here we can run now this Python script. Now we're going to open the text file and also the labels file, okay? Here keep in mind that we define both of them to be the variable d, but we can change the name in here, okay? This is only an example. So let's start with the text. Here we just type with open. Now we define the name of the file that we have just loaded. Keep in mind that this file name is text, so here the file name is text, like this. Then this R in here stands for reading. We're reading this file from the storage, so we just type here R, and then we can type as, and here we can choose any name we want. Here we just type file process, but you can choose here any name you want, okay? And now we just define this list. Let's just name it the same. Here we, on the example, we have D, but here let's just name it the same, text. And now is where we use the JSON model. So here we use this model, and then we load this file in here. So here we just copy and paste in here. So essentially what we are doing, we are opening this file text, we are reading it and storing in here, and now we are using the JSON to transform this file data into a Python object. So this is a list. Very well, so let's test this out. First, let's run this window to import this, this library. Now we run this code. And now here we can create a new code window, and we can, for instance, check the length of this variable text in here, which is this variable that we have just stored. If we run this window, we can see precisely that the length is 4000. This is because we have articles from 4 categories, and each of them has a size of 1000. So 4 different categories gives a total size of 4000 for this text variable. Right now we do the same thing, but now with the labels. Keep in mind that here we need to type the same file name as we have here. This file name is label, so here we just type labels, we are reading this. Here we can maintain the same variable, but now this variable name we want to change it, right? We want to work with different variables, so here let's just name it to be labels. Okay, we run again, and now we can again check what is the size of labels. The size of labels is 4000. Right? And if we check, for instance, what is the label on the document 0, basically which is the category of this document, we see that this is astrophysics. If we check the category of the document with index 999, we check it, we see it is still astrophysics, but now if we change this to 1000, so we have one more, what is going to be? Well, we have computer science. This is because from the index 0 to the index 999, we have a total number of 1000 values, so we have 1000 documents, and here we have all the documents of astrophysics, right? So when we change this index and we move to the next one, this index 1000, we have computer science, right? And we have on computer science to be all of the documents between the index 1000 and the index 1999, because when we change this to 2000, then we will have the other category. We can prove that if we just change now, and first we check the index, this one, which is the last one for computer science, we check, this is computer science category, but now if we change this to 2000, we can easily see this is now mathematics. So essentially what we have on this data set? Well, we have documents, each document belongs to a given category, and we have two lists, one that indicates for each document, okay, we have the category it belongs to, and then for each document, the actual text that this document contains. The actual abstract of this scientific article. Right here, if we just check and we just type text 0, for instance, of the first document, we want to see here the text of the first document. We run, and as we can see, this is the text that this document has. This is the article of this document. It is a, as we can see, astrophysics article, right? Because here, if we just type label 0, this is, as we can see here, astrophysics. Label 0, this is astrophysics. So, what is the objective of this practice? Well, the objective of this practice is to predict what is the category of the document based on its text. That is, given a document, we want to classify this document with its category. So we need to predict if this document is a document of astrophysics, a document of computer science, a document of mathematics, or a document of physics. So we have here in total 4 classes, and we need to classify this document. On the following lesson, we will perform an initial study of this dataset. Hey everyone, on this lesson, we will pre-process our dataset so that we can apply our machine learning models. The reason for this is that not all datasets that are used to generate models correspond to tabular data. In some problems, we must transform unstructured data in some way to be able to use it. And this is the case of the text, what we have on this problem. Before it can be used, we must perform a pre-process that gives us a data matrix on which we can apply a model. So now let's continue where we left off from the previous lesson. Let's add a new text window here. Let's name this to be pre-processing. And now, in this particular case, the usual process follows the following step. First of all, tokenization. What we do here is we split the text into words using either white spaces or regular expressions. Then we perform this step of denormalization. In here, we transform the tokens to a unique format so that the same word, lowercase, removable accents, and others represent the same token. Then on the step 3, we do here something called the elimination of stop words. Stop words are these words that have no meaning by themselves, so we remove them. In the sense, we remove the prepositions, the adverbs, the articles, and more. Then the step 4 is lemmatization. In here, we transform all the words to their root. The step 5 is the reduction of vocabulary to a range of frequencies, so that we don't select neither the most frequent nor the very infrequent range. And finally, the step 6 is the transformation of each text to a feature vector. This feature vector can be binary. This is the word is or is not present in the text. Can also be a counting feature vector. This basically means how many times the word appears. Okay, this feature vector represents how many times a given word appears in the text. And we also have here a very frequent and important feature vector representation, which is here the TF-IDF representation. This is the importance of the word with respect to the set of documents. So here the TF is the term frequency, how many times the word appears in the document, and the IDF is the inverse document frequency. That is, how many documents the word appears. The representation of this text is known as a bag of words, and so we represent each document by a list of words belonging to a vocabulary and an attribute calculated for each of them. So once we have the data as a matrix, then we can apply any machine learning model. So now we need to transform this text data set that we have here, the information of all of the documents. This is document 0, this is the document 1, the document 2, right? We need to transform this into a matrix data set using this representation of bag of words. Now, before pre-processing the text, we will divide this text into a training partition and a test partition. So this technique To divide the data set into training and the test partition is a method to measure the accuracy of a machine learning model, and it is called train and test because we split the data into two sets, a training set and a testing set. With the training set, we train the model, and with the test set, we evaluate the performance of this model. So that we use now the training data to train this model, and now we use this test data that the model has never seen, to evaluate the performance of this model. So to make this partition, we need to import a method from the scikit-learn library. So here we just access the scikit-learn library from scikit-learn, and we access the model of model selection. We import now the method that is called train test split, like this. This will allow us to do this partition. This is a free software machine learning library for the Python programming language, and it features various classification algorithms, including supervector machines. So we are going to import from this library, from this model, the train test split to divide our dataset. So let's run. Once the notebook is up to date, we come here below, and now we just type train test split. So here is the name of the method we have just imported. Now the first argument of this method is the data, basically the text of the documents. Here we have on this list, remember, all of the documents, right? Each position is the document. Here we have the data, and then as the second value here, we have the response variable, also named as the target variable. That is the real class that each document belongs to. Remember that our objective is to predict, given a document, to which class this document belongs to. And we have in total 4 classes: astrophysics, computer science, mathematics, and physics, right? 4 categories. So these categories, these real categories that we know each document to belong, is this variable here, labels. Remember from the previous lesson, right? On these variable labels, we have the category for each document on the dataset. So this is the solution variable, right? So we will design here machine learning models to predict the real values of this solution variable in here. Here we have the data, here we have the solution variable, and then the third argument of this is the test size. Now we are dividing our dataset into 2 partitions, right? A training partition and a test partition. So here we specify the size of the testing, so we also have the size of the training. Now, a common size to choose for the test is 30%, so here we just define the proportion, 0.3. This means that we will have 70% of the size on the training partition and 30% on the test partition. Finally, there is also here a very important argument, which is the random state. And this random state basically means that if we define a given random state, for instance 42, this means that at different executions of this same cell, we will always get the same results. That is, we will always get the same documents to be training or to be test. There will be no different results. If you don't specify this, at different executions of this cell, basically, each time that you execute this cell, you'll have different results. You'll have, basically, you can have a document that before was of the training partition, before this document belonged to the training partition, and now it belongs to the test. We want to avoid that. We want to always have the same division of the documents, always the same result of the partition. So here we define the random state to be 42. With this times, we will always get the same partition when we execute this cell. And now finally, we have here a final argument, which is the argument stratify. And we're going to set this stratify to be equal to labels. Now, what does this mean, the stratify argument? So this argument makes a split so that the proportion of values in the sample produced will be the same as the proportion of values provided to the parameter stratify, in our case, the parameter labels. So to understand this, just consider that we have here a y variable. This is a binary categorical variable with values 0 and 1. And there are 25% of zeros and 75% of ones. If we just set stratify equal to y, this will make sure that our split has 25% of zeros and also 75% of ones in the training partition and also the test partition. So essentially is to have the same proportion as the global data set. Very well, with this we are ready to execute this method. Now this method returns here 4 variables. In fact, it returns a tuple with 4 elements. The first returning value is the data for the training partition, that is the text of all of the documents on this training partition. The second returning variable is the data for the testing partition, that is again all of the texts of these documents of the testing partition. The third one is the target variable for the training partition, that is the real category that each of these documents of the training partition belong to. Keep in mind, this is the same as the labels for the training partition. And the last one is the target variable for the testing partition, that is, for each of the documents that belong to the test partition, the real category that they belong to. Essentially the same as the labels variable for the testing partition. So now we will define the returning values. We have the X train or this data train. Commonly in machine learning, the X stands for data and the Y for the target variable. So here we have X train, we have X test, then we have Y train, Y test equal to this method, like so. So this method we return these 4 variables and we will store them in here. Okay, so let's run this window. Alright, and now we have divided the data set into 2 partitions, the training and the test. So now we can check, for instance, if before the size of the text, if we remember, was, let's say, 4000, what if we type now the size, the length of the training data? So we run, and as we can see, we have 2800. This is precisely 70% of this value, as we stated in here. Since the testing says is 30%, the test size is 30%, and so the training size is 70%. Right, we can check this also for the test. What is the size? Well, now 1200 documents, and we can verify that if we multiply 4000 to 0.3 for this proportion, we have precisely this value, as we can verify in here. And now we can also check the document contents for each of these documents of the training. For instance, if we want to access the first element of the training partition, the first document, the content, this is the content, right? And here, see, we can also check for this same document on the training partition, which class this document belongs to. How? Well, we just type ytrain index 0. So this is the first, the same document as this one, so we just run, and as we can see, this document belongs to the astrophysics. If we now check this one, let's just say 8352, we run, this is this document, and if we want to see what category this document belongs to, we run this, and as we can see, this is computer science. So we have the same structure of the dataset. We have only divided this dataset. We have only performed the partition of this dataset to proceed. Now, on the following lesson, we will perform the real pre-processing of this dataset. First, we will transform the textual labels to numbers, and also very important, we will make the transformation of this dataset to a data matrix. So we will have a matrix. This is what we will do in the following lesson. Hey everyone, on this lesson we will transform our dataset to a data matrix so we can apply our machine learning models. We also talked about this before in the previous lesson. Keep in mind that the dataset that we have is a unstructured dataset, and we need to transform it and apply a pre-processing that gives us a data matrix in which we can apply a machine learning model. So now let's continue where we left off. Okay, here we were on the pre-processing section. Now let's add a new section here, which is the transformation to data matrix. So here we just add transformation to data matrix. You know, before performing this, which is very important, we need to remember and transform the textual labels to numbers. Keep in mind that we have 4 different labels in this practice, right? We have 4 different categories. We have astrophysics, computer science, mathematics, and physics. So now we need to transform these 4 different labels to values that are numerical values. Let's add here a new small section in here, and now to transform the different textual labels that we have on the variable labels to numbers, we need to import a new method here on the import of libraries window. It is a model from the scikit-learn library, so we just access the scikit-learn library, and now we access the pre-processing model, and now the method that we are going to import is a method named label encoder. This method will allow us to transform the categorical labels to numerical values. So let's run this cell. Now the notebook is up to date. We come here below, and now we just type and define first the label encoder. We can just type label encoder, and here we define the method label encoder that we have just imported. And now we want to transform all of the labels from categorical to numerical, right? Remember, on the previous lesson, we performed the partition of the data set, right? We divided the whole data set of the data and the response variable into 2 partitions: the training partition, where we train our model, and the test partition, where we evaluate the performance of the model. So the response variable, that is the labels variable, okay, was now divided into the y-train for the response variable on the training partition, and the y-test, the target variable, for the test partition. Remember that this response variable represents the real category, the real class that the document belongs to. Here we have the solution that we need to predict. So we want to apply the label encoder to both of the training and also the test partition. So now we define the y-train with the label encoder to be the label encoder method, and we use now the fit. So we just type here fit, and the name of the method is fit transform, and here we specify the original categorical label values, which is here the y-train for the training partition. Keep in mind that this method label encoder encode target labels with values between 0 and the number of classes -1. Now this method fit transform fits the label encoder and also return encoded labels. So now we have on this variable in here y-trainl the encoded labels for the training partition. Now we do the same for the labels on the test partition, so we just type y-test l to be the label encoder fit transform, but now we use the testing partition, right? Which is original categorical values. Now let's also define a variable to have the original categorical labels, such that when we want to represent our plots and, for instance, also the performance, we can see the real categories. Not only the values 0, 1, 2, and 3, but also the classes that are astrophysics, computer science, mathematics, and physics. So now let's just type here CLS for the categorical labels, and now we just type here the label encoder, but now instead of using the fit transform, we use a method that is the inverse transform. This transforms labels back to the original encoding, and here we want to select all of the unique different labels of the training partition, for instance, of the response variable. Now to select these unique ones, you need to use here a new function for the numpy library. So we need to import here the numpy library. We just type import numpy as np. Now this library here, numpy, is a very famous and useful library for the Python programming language, adding support for large and multidimensional arrays and matrices, along with a large collection of high-level mathematical functions to operate on these arrays. Now we run this notebook again, and now here we just select the unique one. So we just type here the numpy library, and we use the method unique, and now the y-train labeled like this. Keep in mind, for those who don't know, if you just select this unique method here, numpy unique, and you have the following array: 1, 2, 2, 3, 4, 4, 4, 5. If you have something like this and you run this window, this is going to return the unique elements of this. So only 1, 2, 3, 4, and 5. So we run, and as we can verify, this is the returning array, which is only 1, 2, 3, 4, and 5. It returns the unique elements of a given array. And this is precisely what we are doing in here. Here we have lots of possible classes, lots of possible categories that are already converted to numerical. We have lots of zeros, lots of ones, lots of twos, and lots of threes. We only want here to have 0, 1, 2, and 3, so we use the unique. So at the end we have here that this array is the array 0, 1, 2, and 3. And at the end we transform this 0, 1, 2, and 3 to again the 4 classes: astrophysics, computer science, maths, and physics. Very well, with this we're done. Let's run this window. And now, as we can verify, for instance, if we just check here, we can compare the previous class on the Y train. We have here astrophysics, but now if we use with the label encoder, we see here the class 0. So the astrophysics is for the class 0. Right, in the same way, if we check now the class 1300 on the training partition, this is the class maths. So if we now use the label encoder, we see that this is the class 2. So now maths is the class 2. If we change this to be 800 and we use the original Y train, this is astrophysics. Let's see if we see computer science. So 1800, for instance, we check, we have astrophysics. For instance, if we check the position 2211, we have here computer science. So now if we use the label encoder, we have here the class 1. So computer science is the class 1. So we can establish already this representation of the classes, right? For instance, if now we check and we come here and we check now the position 2788, we see that this is a document of the class physics. And now if we check the label encoded, we have here the class 3, right? So with this we encode the labels. Astrophysics is now the class 0, computer science is the class 1, mathematics the class 2, and finally physics, this last category, the class 3. With this we are done with the textual labels to numbers. Now let's begin the transformation to the data matrix. Now we will consider different ways to transform the text to a data matrix. For this purpose, scikit-learn has 2 special functions for it. The first function is the function count vectorizer, which allows to get the word count, but also the binary representation. And the second function is the tf-idf vectorizer, which calculates the tf-idf of the words. We will start with the simplest, which is a binary representation, so we will use the count vectorizer. Now, we will have to choose a whole set of arguments on how the text vocabulary is pre-processed and generated, some of which we'll leave as default, but they will be part of the hyperparameters that we will have to explore to find the best model. We will modify the following 2 arguments. The first one is the max features. This represents the number of words in the vocabulary. By default, the most frequent ones are chosen, which might not be the best option, so we can control the range of frequencies that is chosen with other arguments. We will try several options. And also the stop words, that we will set this to be English, so we will remove all the stop words that we have on the English language. Now the vectorizer will return a sparse matrix when it makes sense. This will reduce the memory cost, but not all models can work with this representation. But it's important to notice this as well. So let's start doing this transformation. First of all, let's define the vocabulary size. So here let's define voc size. Let's define this to be 1000. For each document, a vocabulary of 1000 is sufficient. And now we define here below the count vectorizer. So here we just use the method count vectorizer. Now this method is a method that is not predefined in Python. We need to import it from the scikit-learn library. So we just go here on the import of libraries window and we access the scikit-learn library. We access the feature extraction period text. model, and we import here the count vectorizer function. Now we run this window. Once the notebook is up to date, we come here below, and now we're ready to use this method. As we've said, we are going to modify these two arguments in here. Remember, the stop words, we can remove all of those words that have no meaning by themselves, such as preposition, adverbs, articles. So here we are going to choose the English language, right? So we are going to remove all of the stop words of the English language. So this is the removal of all of the stop words of the English language. We eliminate them from our vocabulary. Then the second argument that we are going to set here is the maximum number of features. We are going to set this to be equal to the vocabulary size. The maximum number of different words we want on our vocabulary is 1,000. And we also have here an extra argument for the binary representation, that if we set this binary Boolean argument to be true, then all of the non-zero counts are set to 1. So we have a binary representation. Either the word appears in the document or it does not appear. So essentially what we are doing with the count vectorizing user and also using the binary representation is, for each document, imagine this is the document 0, document 1, document 2, document 3, and document 4. We have here a set of words that belong to our vocabulary. We have a matrix, okay, representation that for each document and for each word, we happen to know if this word belongs to this document or not. If this word appears inside this document or not. For instance, the word big does not appear in the document 0, neither in the document 1, but the word big does appear in the document 2. For the word count, the same thing. Okay, not appears, doesn't appear, and here in document 4, it does appear. For the word grade, the same thing. So we have a binary representation. For each document, we know, and we happen to know if a given word belongs to this document or not. Again, this is using binary equal to true. If we set the binary equal to false, if we set the binary argument to be false, then we can have something like this, that for each document we can have that the given word appears more than once. For instance, the word win in the document 1 appears 2 times, right? So here on the count vectorizer, if we set the binary to be false, for each document and for each word, we have the counting, the total number of occurrences of this word in that document. When we set binary equal to true, we only have a binary representation. Either 0 if the word does not appear, or 1 if the word appears, regardless of the number of times. So now, how can we transform our data to a matrix, to have a data matrix? Well, once we have defined the count vectorizer method, then we can just define here the training data vectorized to be the count vectorizer method with the configuration we have just defined, and now we use here the method fit transform on the training of the data. So essentially here we are transforming the original text of the documents. Also, we can do the same thing with the test. We define now the X test vectorized, and we apply the same method with the fit transform, but now we change this for the test. So we transform all the texts of the documents. So we have the count vectorizer representation. So let's run this. So now we can check that we have a data matrix. Here we can just add a new code window. Here we just type xtrain v for the vectorized, and here we can just check the shape of this. So if we check the shape, we see now we have a data matrix with 2,800 rows and 1,000 columns. This is basically the vocabulary. Remember, we have a total number of 4,000 samples in total, and we have 70% on the training and the rest, the 30% on the test. We can also see here that the rest of this 4,000 on the test, we can verify we have here the rest of them, right? 1,200, and we have again these 1,000 columns for the vocabulary. We have a total of 1,000 words because this is the size that we establish as the maximum number of features, right? We have here 1,000 features, and we also remove the stop words. Very important to remove them. If we change this maximum number of features to be, for instance, 1,001, okay, and now we run again as we verify, we have 1,001 columns. We want to work with 1,000 features. This is sufficient, so we work here with 1,000 words. So now we can visualize the vocabulary we have. First, we need to import the word cloud method from the word cloud library. So here we just type from word cloud. We import the method of word cloud. This will allow us to visualize all the vocabulary we have as a word cloud. We run. A word cloud is a visual representation of word data. In other words, it is a collection or cluster of words in different sizes, and the bigger and bolder the word appears, the more often it is mentioned within a given text, and the more important it is. Here we can see two examples of word cloud. This is the first one, this is the second one. As we can see, the bigger the word appears and the more bolder, we have here more importance to this word. So now let's visualize the word count on our vocabulary of this dataset collection. So we define our word cloud as the method of word cloud. We can specify the background color. Let's specify the background color to be white. And we are going to generate this word cloud from the frequencies that we have on our vocabulary. So here generate from frequencies. And here we specify our vocabulary, which is this count vectorized vocabulary. We copy here, we paste it in here, and here we just specify the vocabulary. So we just type here the attribute vocabulary with an underscore at the end. Very well, with this we define the word cloud. Now to visualize this in a figure, we need to import here a new library, and this model from the matplotlib library. So here we just type from matplotlib, we access the pyplot model, so we just type here pyplot, and we want to import this as plt, just like this. Now this library here, the library matplotlib, we need to import, so we just type import. We are going to import this model from this library. This library matplotlib is a plotting library for the Python programming language. And this model here, pyplot, is a state-based interface to matplotlib. It provides us an implicit way of plotting. So we import this library, we run this again. Now first of all, let's create a new figure. We can do this with the pyplot library you have just imported. So here we just type pyplot figure, and we specify the size of this figure. Let's specify a width of 12 and a height of 8. Then to show this word cloud, we just use here the method imShow from this pyplot model. The first argument is the word cloud. We just copy and paste the word cloud. And there's a second argument here, which is the interpolation that we are using. There are lots of interpolations that you can choose in matplotlib. We are going to choose here the bilinear interpolation. Again, you can choose any of this. Also, let's change the name of this notebook to transformation to data matrix. Okay, so here we just change the name to transformation to data matrix. And now here we specify the interpolation to be bilinear. And now when you create a new figure using the pyplot model from the matplotlib library, by default you are going to see an axis, okay, the vertical axis and the horizontal axis. And this figure is going to be a two-dimensional figure. We don't want to display the axis, so we can avoid this. We can just type pyplot, then we type axis, and we define this to be off. So we want to show no axis at all, like this. Okay, very well. So let's run this and let's visualize this vocabulary as a word cloud. Very well. So here we can visualize this word cloud. As we can see, we have this axis description because we set this to be off. If we want to display this axis values, okay, this is basically the values for the axis. If we want to take them out, it is very simple. We just here use a semicolon, and this is going to disappear. So we run again, and as we can see now, it disappears. We have here the word cloud for our vocabulary. This is very important because we can see which are the most present words in these documents. We can see that some common words are here: works, also word is a very common word, but the most common ones we can see here it is yield and zero, right? The most common ones. Then we have here also yield, we have also works, work, version, view, widely, wide, and so on. Now, since we have too many dimensions, we have a total number of 1,000 dimensions, since we have 1,000 columns, right? 1,000 features, 1,000 different tokens in our vocabulary, we cannot do an exploratory analysis of the variables or a detailed visualization. So what we will do is we will use dimensionality reduction to observe and study the relationship between the features and the classes. Remember that here the features are the columns, right? All the different words in our vocabulary, and the classes are the categories. We have 4 different classes. Astrophysics, which is the class 0, computer science, the class 1, mathematics, the class 2, and physics, the class 3. And with this we finish the lesson on the transformation to data matrix. We remind the student that you can download all of this code and all of this notebook on the downloadable documents of this lesson. Hey everyone! On this lesson we will apply dimensionality reduction to our dataset. That is, we have a dataset with a high dimensionality, we have lots of dimensions. Remember, we had a total of 1,000 dimensions. The dimensionality of a dataset is given by their number of columns. And we have a total number of 1,000 columns, right? So we have 1,000 of dimensions. So we also discussed this on the previous lesson. These are too many features. We are not able to visualize these number of features. Humans are only able to visualize 2 and 3 dimensions in a space. So we have 1,000. What can we do about that? Well, we can apply dimensionality reduction techniques. This is a technique where we transform our data set with too many dimensions with a high dimensionality to a lower dimensional space that we are able to visualize. So here we can choose, for instance, 2 dimensions or 3 dimensions. So let's start, let's go to our notebook, let's change the name of this notebook to be dimensionality reduction. Let's add here new text section to be dimensionality reduction. So we just type dimensionality reduction. And now we will start by applying principal component analysis. Principal component analysis is a popular dimensionality reduction technique for analyzing large data sets containing a high number of dimensions, that is, a high number of features, and also this enables the visualization of this multidimensional data. Now, to define our principal component analysis, we need to import this method from the scikit-learn library. So here we just come and we access the scikit-learn library, and now the model that we want to import from is the decomposition model, and we are going to import the PCA method to apply principal component analysis in our dataset. We run this window, we update the notebook, we come here below. And now to use the PCA method, it is very simple. We just define PCA like this. Keep in mind that we are going to apply all the dimensionality reduction techniques on the training partition, right? We want to study the model on the training partition, and then only at the end we will evaluate its performance on the test partition. So here let's define the transform data. Let's just name this T data, or the transform data after applying PCA, after applying principal component analysis. And to do this, we just here copy this method. We use now the function fit transform, and now we need to give or data. Keep in mind this data is on the variable xtrain, right? This variable here, xtrain, v, or the training data vectorized with the count vectorizer. So we can just copy this, we paste it in here, and now here we need to transform this matrix. This is a matrix, as we know, to a dense matrix. We have now that this matrix is a sparse matrix and we want to transform to dense. So here we can just use to dense to transform this matrix to a dense matrix. For those who don't know, if we use this to dense, then we transform this sparse matrix, as we know here, to a dense matrix representation of this matrix. So it returns the matrix with the same shape, containing the same data,
with a dense matrix representation. In fact, we can verify this, right? For instance, if we just type here x train v to dense, we'll see here this matrix. Let's just run. This is a matrix that has, as we know, 2,800 samples, 2,800 documents for the training partition. This is all of the rows we see. Here Python is only showing us the first of them. And as we've said, the idea is that for each row we have here 1,000 columns, 1,000 features. Each feature represents a word, and we have 0 if this word appears in the document or not, right? For instance, on this document here, okay, that we see here, this first word appears because we have a 1, right? On this third document here, this word appears because we have a 1, and also this last word also appears because we have a 1. This is the count vectorizer representation using the binary representation that we studied on the previous lesson. Now, if you try to see this matrix without using two dense, you'll see that this is a space matrix. We want to work with a dense matrix. That's why we are transforming this to a dense matrix. Now, the next thing is to define a data frame for the data. Now, to do this and to work with real data frames in Python, we need to import a very, very important library, which is the pandas library. We can just type here import pandas as pd. Is a software library written from the Python programming language for data manipulation and analysis. So to work with data frames in Python, we need to import this library. So we import now, we come here, and now we define our data frame for the data, right? For the texts. So here we define the data frame for this data. Okay, here when we say data, we refer to the text that each document contains. This is the data. And so when we applied the count vectorizer and the preprocessing, we have here that the data is this matrix in here, that for each document we have 1,000 columns that indicate if a given word appears or not in this document. Now we are going to create this data frame by concatenating lots of them. So here we are going to use the concat to concatenate. This is a method from the pandas library to concatenate data frames. So here the first data frame that we are going to concatenate is the pandas data frame of the transform data, that is the data that we have after applying the principal component analysis. So here we just type transform data. Now, very, very important, we want to select all of the rows. So here we specify all of the rows with 2 points. And now, how many columns will we select? Here, the number of columns that we select our data frame to have basically is going to be the final number of dimensions that we will have. And on a dimensionality reduction technique, we can reduce our data set with a high dimensionality to 2 possible options. Either we reduce to 3 dimensions and we visualize our data in 3 dimensions, or we reduce with 2 dimensions and we visualize the separation of the data, depending on the class and on the category, with 2 dimensions. For this lesson, we're going to choose here 2 dimensions, but again, you can use 3 if you want. So to have the first 2 columns, the first 2 components of the principal component analysis, okay, you'll normally hear when you talk about here dimensions in principal component analysis, you're really talking about the number of components. That's why the name is principal component analysis. We take the first principal components to be the number of dimensions. Keep in mind that this is going to select the first 2 columns, the column 0 and the column 1. Keep in mind that if you have a list like this and you just type L 2.2, you're going to select the first 2, right? The index 0 and the index 1. As we can see, these returns 1 and 5, the first 2 elements. So here we are selecting the first 2 components, right, of the principal component analysis. And we want to concatenate all of this data to here now the real class that each document belongs to, the real category that each document belongs to. So here we know that this is on the yTrain variable, remember? Okay, this variable here, yTrain, we have the real category for each document, right? Now this variable y was already transform to have numerical values. Initially it had categorical values, right, as to physics, computer science, mathematics, and physics. Now we have 0, 1, 2, and 3 for these 4 different classes, these 4 different categories. So we want to concatenate this with now the pandas data frame of the Y train. So here we are going to define this data frame as a dictionary, where the column name is going to be labeled and the values are going to be the Y train. When you want to define a dictionary in Python, you just open a curly bracket between strings. Here you define the key value. Keep in mind that you can also have integer key values, and then you use 2 points and the value of this key. At the end, you return or basically close this curly bracket. Now, since we're using the concatenation of these 2 data frames, we need to use here square brackets. So we open and we close like this. Now, this method from the pandas library formally concatenates pandas objects along a particular axis. This axis could be index or columns. And here, if we specify the axis to be 0, it means that we're concatenating by index. If we specify the axis to be 1, it means that we're concatenating by columns. We want to concatenate by columns. So here, we specify the axis to be 1, like this. So in that sense, we'll have the 2 components, the 2 dimensions of the data, and then we'll have concatenated the column of the response variable, right? The real class, the real category that each document belongs to. With this, we will be able to visualize the separation between the classes, the separation between the categories for all of the documents. This was pretty much the work that we had to do here. Now we only need to create a new figure to visualize this. So we just use pyplot figure. Let's specify a figure size, for instance, of 8 in width and 8 in height. And now to visualize this separation between the classes, we will use a scatter plot. To be able to apply a scatter plot, we are going to import the Seaborn library. So here we just type import Seaborn as SNS. This is a Python data visualization library based on matplotlib. It provides a high-level interface for drawing attractive and informative statistical graphics. We are going to use this library to make scatter plots. So let's run. Very well. Now, for those who don't remember what is a scatter plot, we can just type here SNS scatter plot. With this, we are going to build a scatter plot inside this figure. Now, a scatter plot and scatter plots are used to plot data points on a horizontal and vertical axis to show how much they are related. Keep in mind that we can also have a 3-dimensional scatter plot, such that we will also have here a depth axis. In our case, we're working with 2 dimensions. So here we specify the axis. We will have the x equal to 0, the y equal to 1 as base vectors. 0 for the horizontal and y equal to 1 for the vertical. And now very, very important, what is going to be the hue? That is, what is going to be our separation criteria? This is the variable that will produce points with different colors. That is, keep in mind what we want to visualize now, and the point of this is to visualize the separation between the classes, the separation between the categories. We want to see how different they are, right? We want to see, if we pick a document from astrophysics, which words are likely to be in, which words are likely to be in computer science, which words are likely to be inside a mathematics document. This is what we want. So here the separation criteria, the variable that will determine the colors of the data points in this scatter plot, is the response variable. Precisely the categories, the classes. And keep in mind that these classes here, the real categories that each document belongs to, is this column here labeled. So since we have this data frame, we want this column to be the hue, this column to be the separation criteria. This is very, very important to understand. It's the most important thing of this lesson. Now here we just specify the data frame that we're going to work with is this one. So we just copy data frame data, we paste it in here. And now next, and the last thing, we can also define the palette. The palette is basically the method for choosing the colors to use when mapping the hue. So there are lots of them in Seaborn. We're going to use, for this example, the tab 10 palette. This is a common palette used, but you can If you have another, you can here choose the other that you have. Again, there are lots of them. Very well, with this we are ready. Let's see now the visualization and the separation between the classes. Let's run. And as we can see, here we have a two-dimensional representation. Since we are using two components, we have two dimensions, okay? This data set, this data frame has only two dimensions. And then the response variable, right? Which is essentially our separation criteria. And now as we can see here the clusters for each category, the clusters for each class. We can easily see that they are not all together, but they form this sort of groups, these sort of clusters. So what does this mean? To understand what this means, it is very, very important, right? Almost even more to know how to plot this. So the interpretation of this is the following. If we have groups here and clusters for each category, it means that each category, each class that we have, astrophysics, computer science, maths, and physics, will have its own set of words that will be most likely to be inside that document. Essentially, if we take a document from astrophysics, for instance, this blue in here, as we can see, this data point in here, and then we take another document from maths, this one in here, and if we compare the set of words that appear in both of them, there will be most likely a very low similarity. They will be very, very different. That's what this visualization of this separation of the classes represent. It is very important to understand this. It is saying that depending on the category that you choose, you will have a set of words that will be most likely in this category. Now, of course, there are some words that do intersect. This is easily seen in physics, okay? Here, the category of physics intersect with all three clusters, and also there's an intersection between computer science and maths. So, for instance, this intersection between computer science and maths basically represents, if we take a document of maths and a document of computer science, they might have a considerable amount of similar words. There will be a considerable amount of words that will appear both in computer science document and also in the maths document. Also, this intersection of physics and the rest of them. If we take a document of physics and a document of astrophysics, for instance, there will be also a considerable amount of words that will be in both of these documents. So they will share some similarity. Basically, their rows will be, as we can see, similar, right? Because essentially, if we have two documents that have the same content of rows, or basically the same content of columns, right? It means that they have the same words. This can only happen if we have the same document or a sub-document of another one. So essentially, this is very important to visualize and to understand this visualization. Now we can conclude and verify and also prove that these categories form clusters. Each category has its own set of frequent words that appear. Very well. With this, we end this dimensionality reduction lesson, where we visualize the relationship between the features and the classes, that is, the relationship between the set of words that can appear in each document and the categories. There are more dimensionality reduction techniques. Principal component analysis is just one of them. For now, we are just going to leave this one, which is far more than sufficient. And on the following lessons, we will start applying supervector machine models. Hey everyone, on this lesson we will use the supervector machine with linear kernel to predict the category, that is the class, that each document that we have on the dataset belongs to. Remember, the objective of this practice is given a document, which category this document belongs to, and we will predict this based on the information of which words appear inside this text, inside this document. So now let's continue where we left off. Let's change the name of this notebook to be supervector machine with linear kernel. So remember from the initial lesson, the idea of a supervector machine is to find the optimal separator between the classes that will correspond to the hyperplane that maximizes the margin between them. If the classes are not linearly separable, as probably happens in our case, we can put a limit on the error that the classifier makes to make this separator and to find this separator. We can use different kernels that increase the dimensionality of the space to more easily get the separator. Now, what is a kernel in machine learning? Well, the word kernel is used to refer to the kernel trick. This is a method of using a linear classifier to solve a non-linear problem. Hence, it entails transforming linearly inseparable data, like this one on the left, to linearly separable ones, as this one on the right. This is what is used as the notion of the kernel trick, or just kernel. There are different types of kernel. On this practice, we will work with the linear kernel, also the supervector machine with polynomial kernel, and the supervector machine with the radio basis function kernel. So we will start by using here the linear kernel. Now, very important, before using it, the usual thing is to normalize the data to use this supervector machine. So in our case, we don't need this since our data is a binary. Either we have a 0 in our table, or we have a 1 if this given word appears on this given document, right? Here, if we visualize this dense matrix of the data, we can see that we have either zeros or ones, depending if a given word that represents this column appears on this document, right, that is represented by this row. So here the samples, the documents, are the rows, and the columns are the words. If we have a 1, the word appears in the document. If we have a 0, it does not appear. Now, since we have a binary problem, we need to import here from this scikit-learn library. So we access again the scikit-learn library from scikit-learn. Now we access the model of supervector machines. Here we have all of the supervector machines that scikit-learn provides, and we are going to import now the supervector machine, that is SVC, for super vector classification. Keep in mind, since we have a classification problem, right, here we need to use a supervector machine for classification. You can also import, if you have a regression problem, you just type here import SVR for the regression with the same model, okay? For this practice, we are on classification, so here we import this classification method. Very well. Now, when we type SVC for supervector classification, there's an argument called C. This argument here tells the supervector machine optimization how much we want to avoid misclassifying each training example. Now, we need to perform here a search, a exploration for the best argument of this C to get the best score, since we don't know beforehand which value is the best, since this depends directly on our dataset. For instance, what if we here pick a low argument C and here we pick a large argument C? We have the same dataset. As we can see, the best result, the best separation of the classes happens when we take this large C. Does this mean that we always need to take a value of C that is very large? The answer is no. Since what if we have this dataset now? We can see here if we pick a value that C, or a big value of C, and we pick a low value of C, this small value is better, gives us a better separation of the classes than this one. So this depends completely on the problem and completely on our dataset. That's why here we are going to perform an exploration. Remember, we can define these possible values for the C as a dictionary. So here let's define the dictionary param for parameter. Here we specify the name of the argument, this C. And now we want to check here all of the values between -10, or essentially here 10 raised to -3, up until 10 raised to 3. So we want to check evenly spaced numbers inside this list. We can easily do this with a numpy linspace. This returns evenly spaced arrays. Here the starting point is -3. The ending point is 3, and we want a total of 800 samples, so here we just specify 801, and now we just raise this to the power. So here we will have 10 raised to -3, then 10 raised to the next one, and so on, evenly spaced values up until 10 raised to 3. We can verify. Here we see a total number of 800 values, okay, which is all of the values evenly spaced between 10 raised to -3 and 10 raised to 3. So these are the possible values that this argument C can take that we will do now this exploration. So now let's define the linear supervector classification model. So here we just type linear supervector classification. Now we define the model just typing SVC, the method we have just imported from the scikit-learn library on the models of supervector machines. Here we specify first the kernel. The kernel is going to be linear, as on the first lesson, right? As we are in here. Then the next argument is the maximum number of iterations within the solver. Here let's set a limit of 25,000, this is sufficient. And also very important, we need to specify a random state such that different executions give us the same result, right? We don't want here to work with different results in the same way as we did on the partition of the dataset. We always want to have the same results as we keep executing the cell over and over. So here let's define a random state to be 0, for instance. And let's now perform the exploration, this search. So let's just define here the linear super vector classifier search. So here from the library of scikit-optimize, we are going to import the Bayer search for cross-validation as well. Now this library scikit-optimize implements several methods for model-based optimization to perform this Bayesian search, this Bayesian optimization over hyperparameters. Now, to be able to import this scope library, we need to now install the scikit-optimize in the following way. We just type pip install scikit-optimize. This here is needed to work with scikit-optimize. So we run this window, we wait for the installation, and now we are ready. We come here below, and we perform this Bayes search with cross-validation. So we will explore the best scores with cross-validation. Cross-validation is a technique in machine learning for evaluating models and testing their performances. So essentially what we do is we partition the training data into different splits. We can choose here the number of splits, and then for each of these folds, we are going to choose one fold to be the test set. So here on this split 1, the fold 1 is the test data. On this split 2, the fold 2 is the test data. We calculate the final score of all of them, and then we calculate the average. This is how cross-validation works. So, on this Bayes search, the first argument is the model. So here we just specify the linear cross. Here the supervector machine for classification, this model. The second argument is basically the parameters or the parameter that we want to optimize. In this case, we only have C, so we copy this variable and we paste it in here. Then we also can specify the number of iterations. Let's specify here a number of iterations to be 15. Then we can also select the number of splits along with the folds. So let's use the same as we saw in the figure. Let's choose here a cross-validation number of splits of 5. Then we have here an argument which is a number of jobs. This is the number of jobs to run in parallel. Now if we select -1, it means that we will use all the processors. This is precisely what we want to optimize also this speed of this search. So we also have less time execution. Then we have here Boolean argument which is refit, that if we set this argument to be true, then after searching for the best parameter, we are going to refit this best estimator, this best argument with the entire data set. Okay, and this is what we can do after doing this Bayes search. Finally, as we defined the random state before, okay, we can also here use the random state. Let's use the same one and choose here to be 0. Once we perform this search, we already know the best estimators, and now we fit. So now we just type here fit, and now we give as the first argument the data. This data is, as we know, X-train vectorized, and then we give the target variable, the response variable, Y-train, with the L suffix. Remember that this L here is when we transform these textual labels, astrophysics, computer science, mathematics, and physics, to numbers, to the class 0, 1, 2, and 3. So now when we select Y-train L, we have this column, the response variable for the training partition, where the contents are numbers. Okay, the class 0, the class 2, 3, 1, and so. Very well, so let's run this. We wait for the Bayes search to complete the exploration. This can take some time, since it is testing all of these values and also the score. Alright, it already finished. It lasted around 3 minutes, and this is completely normal. Don't worry if your execution takes this amount of time. This is completely what is supposed to be. Now, once we know that this has the best estimator, how can we check and see the real value of this C that we have just found, right? We want to see what is this value, and also what are the best values sorted. So to do this, we'll need to here show and implement a show HTML method. So we go to the windows of libraries, and now we access the model display of the IPython library, and we simply define this show HTML method in the following way. Given a HTML object, we are going to display this object as a HTML class. With this, we will be able to visualize the best results. So we run again this window, do not forget. Okay, so here we are going to show the results of this search. So we just here create a new pandas data frame. We just type pd data frame upon the results of this. So here we just type CV results, since this is a cross-validation result. And from this data frame, we want to select a group of rows and columns by label. So here we just type period log to do this. We want to select all of the rows, all of the results that we have found. Then on the columns, we want to select on one side the parameters column, also the mean test score, and finally the rank test score. And we want to sort these values by their rank. So here we just type period, we specify the column that we want to sort. We want to see the first 5 elements, so we just type here head of this pandas data frame, and we transform this to HTML. So here we just type to HTML. So now we remove this parenthesis, and also we add the last one in here, and we run this. And now, as we can see, we have your list of the 5 best values for this argument C, which is the argument that tells the super vector machine optimization how much we want to avoid misclassifying each training sample. And we see that, for instance, if we take a value of C 0.0138 or less, we have a mean test score of 0.783. But if we take a value of C to be 0.0079 more or less, we get a mean test score that is 0.782. So it is a smaller score. So here the rank 1, the best estimator and the best argument C here is this value that we see. You can also here check all of them. If in the head you just put here 15, for instance, in this head, then you'll see the first 15 elements, okay? We're mainly interested in the first one, so here to visualize the first 5 is sufficient. So up until now, we will work with this value for the C argument, and this value is already now inside this model. Remember that we are setting the refit to be true, so at the end, after performing the best search, we have here the best estimator. So now let's perform the classification report of this model, of this super vector machine with linear kernel. The classification report is a report showing the main classification metrics, such as precision, recall, the accuracy, the F1 score. So we need to import from the metrics model of scikit-learn. So here we just type scikit-learn metrics. We are going to import the classification report. We update the notebook. And now in here, to print the classification report, it is very simple. We just type print classification report. Here we specify as the first argument the model of the super vector machine for classification with linear kernel that we have used for the search. So here we have the best estimator. We copy, we paste it here, and now we predict. And this is where we are making the prediction. So now we are testing the model performance. We need to use the test partition, the test set. So we are going to predict with the information of the X test vectorized. This is basically the test partition of all of the data. Okay, here we have a list of the documents that belong to the test partition. And for each document, for each row, we have a list of words that appear inside this document, right? This is the data that we use to make the prediction of the category. Now, the second argument is the real class, the real category that this document belongs to. So here we just type y test with the L with these values 0, 1, 2, and 3. Right here we have the real categories that each document belong to in numerical value, class 0 for astrophysics, class 1 for computer science. And then finally we specify as optional the target names, that is the name of the classes. Remember that the category names of the classes were astrophysics, CS for computer science, math, and physics, right? So here we need to set them. Remember that when we perform the label encoder and we transform the textual labels to numbers, right, on the solution variable, we also here maintain a variable that has all of the categorical names of these categories. So here we have the category names of the classes. Here we have astrophysics, maths, computer science, and physics as we were given initially. So we copy this, remember that we did this on the transformation textual labels to numbers. So we also want to maintain the same labels of the names, so we just paste it in here, like so. Very well, and with this we are ready, so let's run. Good, so here we can see all the metrics of our predictions by each different category, right? For instance, for the astrophysics class, for the astrophysics category, we have a precision of 0.86, 86%, a recall of 0.9, a 90%, and then an F1 score of an 88%. Now this column here, support, is the number of actual occurrences of the class in the specified data set. Keep in mind that since we have on the test partition a total number of 8,200 documents, if we sum all of this, we have this total value. So in the class astrophysics, the supervector machine with linear kernel has predicted that there are a total of 287 with this F1 score, and the same for the rest of the classes. Now, when analyzing the performance of a model, regardless if this is a supervector machine model or another machine learning model, you will always look at the F1 score, okay? In most of the cases, this is the most complete metric among these two. In the past, what was used was the average between those two. Basically, we sum this value plus this value and we divide by 2. So we calculate the mean. However, this was not useful at all. And then it was introduced this F1 score. This metric is defined like this. We have 2 multiplied with the recall, multiplied with the precision, divided by the sum of this. And this is the most complete metric that we need to see, okay? When we have values close to 1, we have values that are close to perfect. When we have values close to 0, we have very bad performance. Very simple. This ranges from 0 to 1. So as we see, the astrophysics articles seem to be the ones that rank best in this prediction model, using this supervector machine. Now let's visualize the confusion matrix. This is a very important visualization in any classification problem. Either if we have a binary problem, we have only 2 classes, 0 and 1, or if we have a multi-class problem, if we have more than 2 classes, which is our case. Both of the cases we will always use confusion matrix in classification. Now, when we have lots of classes, the confusion matrix for multi-class classification is used to know the performance of a machine learning classification model. It gives a comparison between the actual values and the predicted values. Now, here to plot the confusion matrix, we need to go on the import of libraries window. And on the metrics model of scikit-learn, we just here import the confusion matrix display, like this. We run again. Once the notebook is up to date, we are ready here. We create now a new figure. First of all, using pyplot, let's specify a figure size of 8 by 8. And now here to plot the confusion matrix, we just type confusion matrix display, and now we use the method from the estimator. We take our estimator, which is this one, lsvc search, so we just paste it in here. Then we pass the data and also the response variable on the test partition. So here we type xtest_v, the data, and then the response variable ytest_l to be numerical values. Finally, in the same way we want to visualize these labels, right? Here there's a method that instead of target names, we use display label. So here display label is equals to CLS. So we'll see astrophysics, CS, math, and physics. Finally, there's a last argument here, which is the axis of this matrix. We are going to take the first and the same axis of this figure that we have just created. So it is a subplot of this figure. Okay, so let's run. Alright, and as we can see, here we have the confusion matrix for the support vector machine with linear kernel model. When making the prediction of this practice, which is to predict, given a document, which category this document is in. So, how can we interpret this matrix? Here we have a multi-class problem. This means that we have more than two classes, and the interpretation of the confusion matrix is different if we have a binary problem or if we have a non-binary problem, a multi-class problem. So we are going to explain only the interpretation of the multi-class problem, which is our case. So this confusion matrix has first the true label. Okay, this vertical axis is the true label, and then we have here the horizontal axis, the predicted label. So we interpret this in the following way. Among of all the astrophysics documents that we have predicted, how many of them are really astrophysics documents? So as we can see, among all of them, we have 259 documents that we predicted as astrophysics documents. So this is the amount of true positives, right? The amount of true astrophysics documents that we have predicted. Now, among the astrophysics predictions that we've made, how many were computer science documents? 0, none of them. Now, as we can see here, how many of the astrophysics documents that we predicted as astrophysics were in actual and in reality math documents? 1. This 1 means that we have predicted a document to be in the astrophysics category, but this document really was on the math category. So we can see we predicted the document to be in the astrophysics category, but in reality this document was on the math category. And then the same thing here. How many of the astrophysics predictions that we made these documents and we predicted them to be astrophysics were in reality physics ones? Well, 27. We have here 27 documents that we predicted as astrophysics that in reality they were physics documents. They belonged to the category of physics. This is how we interpret this, and the same for the rest, right? How many computer science predictions that we've made were two computer science documents? Well, 215. But as we can see, we predicted 5 documents as computer science documents, but they were astrophysics. We predicted 39 documents as computer science documents, but they were math documents, and so on for the rest. So with this confusion matrix, we can conclude that the physics articles are the ones that have the most confusion with the rest. Those of astrophysics are not too similar to those of computer science or mathematics, and there is also some overlap between these last two. Another very important metric and plot to visualize when working in classification problems is the receiver operating characteristic curve, or just the ROC curve. This is a measure of a classifier's predictive quality that compares and visualizes the trade-off between the model's sensitivity and specificity. When we plot, this ROC curve displays the true positive rate on the y-axis and the false positive rate on the x-axis on both a global average and per class basis. So the ideal point is therefore the top left corner of this plot. False positives are 0 and true positives are 1. Now this ROC curve leads to another metric which is very important. This is a scalar metric. This is the area under the curve, which is the computation of the relationship between false positives and true positives. This is a value between 0 and 1, and we also want here to maximize this value. So the perfect value of this area is 1, which represents a proportion of 1 of true positives and close to 0 false positives. Now to plot this ROC curve, we need to import from the yellow brick library the classifier model. We access ROC-out, and we are going to import now the ROC-out method. Yellow brick is a library in Python that can help to evaluate the performance, stability, and the predictive value of machine learning models. We are going to import this library here, this method, to plot the ROC curve. So we run. Once the notebook is up to date, we come here below, and now we just type, to first create the figure, we just type plot figure, the figure size to be 8.8, like before, and now to plot the rock curve, we just type the method we have just imported, rock_alg. Now the first argument is the name of our model, so this model is this one, as we know, the linear supervector classification with a search that we have done before, so we just pasted this. Remember, this is the supervector machine with the best value of this argument C, as we did on the exploration. And then we specify the data for the training set, so here we just copy and paste. Then the response variable for the training set. Then the data for the test set, so here we have test. And then finally the response variable, the target variable for the test set, so y test L. Very well, with this we are almost done. Now finally we just need to specify the different classes that we have. We have astrophysics, computer science, maths and physics. So here we specify the classes to be this variable CLS for the classes that we have and as we define on the label encoder. So now let's run. Very well, and here we can see the raw curve of all of the classes, the astrophysics class, the computer science, the maths and the physics. Now remember that the area under the curve that we wanted is to be 1, right? So as we can see, when we are working on the astrophysics predictions, this area under the curve is 0.98, so the best so far, as we did on the confusion matrix, right? Then the computer science 0.93, the maths 0.92 and the physics 0.88. So in the raw curve we can also see that the astrophysics documents are the ones that are best distinguished with this supervector machine model. Very well, with this we finish this lesson of the supervector machine using linear kernel. We have achieved our objective, which is to predict for each document in our dataset to which category this document belongs to. We studied the performance of this supervector machine model and also we visualized the metrics. On the following lesson, we will use supervector machines with polynomial kernels. We remind the student that you can download all of this code and all of this notebook on the downloadable documents of this lesson. Hey everyone, on this lesson we will use support vector machines with polynomial kernels to predict the category, that is the class that each document in our dataset belongs to. So if you remember from the previous lesson, we used a supervector machine with a linear kernel. We studied the performance with the classification report, the confusion matrix, and the raw curve. Let's add now a new text section here. Let's name this section to be polynomial kernels. We will use quadratic and cubic polynomial kernels. Now, to use this supervector machine with polynomial kernels, we will search the best values for the following arguments. First, the argument C. This is the first argument that we explored and we searched for the best value before on the linear kernel. Okay, basically this represents how much we want to avoid misclassifying each sample on the training set. And then we will also search for the best values of this degree, okay, the degree of the polynomial kernel function. Since we will now try and see and check which of these two are the best. We will try with the quadratic kernel and also with the cubic kernel. So we will have here degree 2 and degree 3, right? And now let's gather the exploration and find out which is the best, the quadratic kernel or the cubic kernel for this problem. So let's start finding these best values for the parameters. Here we specify the same way as a dictionary. Here first we have C. We can just copy this from the previous lesson. So here we define the arguments. And now we have C, but we also have the degree. So now in this dictionary we can also here add a new element that we want to optimize, which is the degree. And now this value can be 2 for the quadratic kernel or cubic for the this cubic kernel, right? So here, if we set 3, we have the cubic kernel. If we set 2, we have the quadratic kernel. So we can have 2 or we can have 3. Okay, so now let's define the polynomial kernel. So here we just define polynomial supervector machine for classification. So here we just use polynomial supervector classifier. We use the method that we have imported in the previous lesson, supervector classifier from the scikit-learn library. Now here we specify the kernel. Since we have a polynomial kernel, we just use here poly or polynomial. Then we specify the maximum number of iterations. Let's here choose a value of 25,000. And finally, we define the random state to always have the same results regardless of the executions that we make. So we can have here press this button several times, we'll always have the same result. Let's define the random state to be 0. Now this is the model of the supervector classifier with the polynomial kernel, but we want to search on this model the best values for the C argument and the best values for the degree argument, okay, between 2 and 3, and this C between 10 raised to minus 3 and 10 raised to 3, as we explained on the previous lesson. So now we define the polynomial supervector classifier with the search, and here we are going to perform a base search with cross-validation, as we did before using the linear kernel, right? In fact, we can just copy this. Let's copy this. Let's minimize this, and we paste it in here. And the initialization is the same. We just here change this model of linear supervector classifier to polynomial vector classifier, which is now this one, right? Keep in mind that here we have the model of the supervector classifier. Here we have the arguments that we want to optimize using this base search. Here we have the number of iterations, 15, the number of splits on the cross-validation. We also reviewed and explained what was cross-validation on the previous lesson. Then we have this argument number of jobs. This is how many jobs we want to run in parallel. If we set this to be -1, then we will run with all processors. So with this, we'll have the most efficient search. Then this refit, we set this to be true, so that at the end, when we have the best estimator, we can have this estimator inside this variable. So this is the final model. And here we define the random state for the same reason as before. We want different executions to have the same result, so here we define a random state. At the end, we just type the name of this model, which is here PSVC search. So we copy, we paste, and we use the fit method on the training partition. Remember, we're training our supervector classifier right now, okay? So we need to work with the training partition. This is the data of the training partition. Basically, for each of the documents that we have in the training partition, we have a list of which words appear inside this document. And then we have here the response variable, which is the real category that each document belongs to. Okay, so with this we are ready, let's run. Again, this can take some time, and it is completely normal. Okay, it already finished the execution. In our case, it took around 3 minutes. So now, once we have done this exploration, how can we see which are the best results for these values C with this degree that we see in here? So we can visualize them as with the function showHTML, and this is the function that we defined on the previous lesson, right? Here we have this function defined. We import from the IPython library the display model, we import the display HTML, and here we define the showHTML this method as a lambda function that given a HTML object, we're going to display it, right? It is simple as this. So now we can just copy the same initialization that we did on the linear kernel. We copy this, we now minimize, we paste it in here. And now the idea is we only need to change the name of this model. Instead of linear supervector classifier search, we have polynomial supervector classifier search. We check the cross-validation results and we sort by their rank, right? So we can run this. Alright, so here we can see the 5 best values, okay, for both the C argument and the degree. So for instance, if we take a value C of 1.5135 more or less, and we take a quadratic kernel, so here the degree is 2, right, we have a mean test score of 0.785, and this is, by this exploration, overall, the other argument is the best set of arguments, so we get the best mean test score. We can see this by the rank. The rank of this test score is 1. It is the best one that we can get. This is the values that we need to choose. You can also visualize more, okay, estimators. Here you can just change this head to be 10. Okay, if you specify the argument 10, then you can see the first 10 best ones, as we can see here. We have now 10 different values for the C and the degree. We are going to choose this first one as we've said. So here we can just see and visualize the first 5 ones, and we are going to choose this one. So now this configuration is now retained inside this model polynomial supervector classifier search, and we can conclude that now this model here is a quadratic kernel. Okay, now let's display the classification report. So here, let's add a new text section. Let's just name this classification report. Remember, in the classification report, we can visualize the results of the precision, the recall, and the F1 score of each of these 4 categories, each of these 4 classes. So to print this classification report, we do it in the same way as we did on the linear kernel. So we just go here, classification report, we copy this instruction, and now here we just paste it. And now we only need to change the name of this model. Instead of linear kernel, we just use here polynomial supervector machine. We are going to predict using this information, and here we have the real values. Remember that now we need to do this with the test partition, not the training, because now we are evaluating the performance of this model. Okay, the train was done in here, and now here we evaluate the performance. In fact, the train is done in this fit. Okay, in this fit function is where we do the training, and here we are evaluating the performance. So we are going to predict these values, these real values, using this information. Remember that the target names, this variable CLS, is basically a variable that has the names of the classes. So we run, and here we can see the results of the precision, recall, the F1 score for each of these 4 classes, using a supervector machine with a polynomial kernel, in fact, a quadratic kernel, since the degree is the degree 2. Remember, the most important metric is the F1 score, and this is a value that ranges from 0 to 1, and we want 1, always, since 1 is a perfect model, so we want to have values close to 1, right? If we have a model where the F1 score is close to 0, it means that this is not a good model. If we have an F1 score that is close to 1, it is a good model. And also remember that these support columns, these last column support, basically represent the number of actual occurrences of the class in the specified dataset. So here we have predicted a total number of 281 documents that belong to astrophysics, 289 for computer science, 336 for maths, and 294 for physics. Keep in mind, since we have a total number of 1,200, if we sum all of these 4, we get this value, right? So now let's compare this supervector machine with the previous one using linear kernel. Let's compare the F1 score of these classes. So now we're going to put the classification report of the previous model, the linear kernel, here below, so we can compare. So as we can see, on the astrophysics class, we have the same F1 score. On the computer science, we have improved the F1 score, okay, from 0.73 to 0.74. On the maths class, we have 0.75 now, so before we had 0.76, right? So we decreased the F1 score, and finally on the physics, we have the same F1 score. Okay, so if we check the global accuracy of this model, this final value for the F1 score, for all of the classes, we have the same, 0.77, 0.77, right? So this is the comparison between the previous one. So now let's show the confusion matrix of this polynomial kernel, of this quadratic kernel. Remember that this confusion matrix gives us a comparison between the actual and the predicted values. So let's display this confusion matrix. We can just copy what we had from the previous lesson. Here it is the same snippet that we have, so here we can just copy this. Now we minimize this and we paste this snippet for the confusion matrix. We first create a pie plot figure. The size of this figure is 8 by 8, and now we display the confusion matrix with this method that we imported from the scikit-learn, right, from an estimator that we have already. This estimator is now the polynomial supervector machine search. Okay, keep in mind that this model contains these arguments in here. Basically, it is an estimator with the best values of the arguments that gives us the best score with the best rank. So now we apply this search. You know, here the test is what we use. First is the data. with this data, we predict these real values, right? So here we have the information that we use to make the predictions. Here we have the real values of the classes, and here we define the labels to display the names of the classes. And finally, the axis is the same as the figure we have just created. So now let's run this. Very well, so this is the confusion matrix. Remember the interpretation of this confusion matrix. It is very important to understand what this matrix is telling us. We need to interpret this as following. For the astrophysics documents that we have predicted as astrophysics documents, right? How many of them were actual astrophysics documents? Well, we can see that 257 were in reality astrophysics documents. So we have a lot of them. Then for the documents that we have predicted as astrophysics, how many of them were computer science documents? 1, right? For the astrophysics prediction, how many of them were maths? 0. And now here finally we have, for the astrophysics predictions, how many of these documents that we predicted as astrophysics were in reality physics documents? 23, right? And the same goes for the rest of the columns and the rest of the categories. So now let's compare this confusion matrix for the supervector classifier with this polynomial kernel from the linear kernel. So let's copy the confusion matrix of the linear kernel below. So here we have the confusion matrix of the linear kernel, and here we have the confusion matrix of the polynomial kernel that we have just used. So as we can see, these values on the diagonal are the values that are right, the values that are correct. Essentially, they are the correct predictions. So we want to maximize this value. So let's compare. If we compare the previous linear kernel with this one, with the polynomial kernel, we have lost something in the astrophysics documents from 259 correct predictions to 257. But if we compare the rest, remember, before of the correct predictions of computer science were only 215, now we have 219. And also, of the maths, before the correct predictions of math documents was 238, and now it is 239. So we also gain of these two classes. Finally, the physics class has the same number of correct predictions in the linear kernel and on the polynomial kernel. So we can see from this polynomial model, we have lost something in the astrophysics articles, only 2, but we have gained something in the rest of these two classes, computer science and maths. Let's now plot the ROC curve of this supervector classifier with polynomial kernel model. This curve, remember, represents the trade-off between the true positive rate and the false positive rate. This leads to a new metric in this plot, which is the area under this curve, the AUC. This is a value that ranges from 0 to 1, and we want this value to be as close to 1 as possible. This means that the true positive rate is much greater than the false positive rate. Now to plot this ROC curve, we can just copy the snippet that we have done on the previous lesson. We just go to the ROC curve, we copy this snippet, we add a new code window here, we paste it in here, and now we just change the name of this model from the linear supervector classifier to polynomial supervector classifier with the search, right? Here, remember, we are using a function from the yellow brick library that we imported also in the previous lesson. Here we need to give the training partition, the data and the response variable, and also the test partition, the data and the response variable. So let's run this plot. Very well, and as we can see, we have a area under the curve of the astrophysics class of 0.98, for the computer science for 0.93, maths 0.92, and physics 0.88. Keep in mind, in the ROC curve, the more the curve is closed to this upper left corner, the better. That's why here the astrophysics has the higher value. It is the closest to this top left corner. So if we compare the ROC curve from the previous one on the linear kernel, we can see this ROC curve also had 0.98, 93, 92, 88. Therefore, we can conclude that the ROC curves, both of them, linear kernel and polynomial kernel, are pretty similar. Very well, with this we finish this lesson. Let's change the name of this notebook to be Supervector Machine with Polynomial Kernels. On the previous lesson, we studied the linear kernel supervector machine. On this lesson, we work with the polynomial kernels, and on the next lesson, we are going to use the supervector machine with the radial basis function kernel. We remind the student that you can download all the code that we have used on this lesson and all of this notebook on the downloadable documents of this lesson. See you on the next lesson. Hey everyone, on this lesson we will use the supervector machine with the radial basis function kernel to predict the category that each document belongs to. On the previous lessons we used the supervector machine with linear kernel and with polynomial kernel, and so now let's add a new text section in here for the radial basis function kernel. Now this kernel is a kernel that we need to specify, and we will search for the best values of these two arguments. The first argument is the argument C. This is one we already seen on the previous lessons, right? Basically it tells the supervector machine optimization how much we want to avoid misclassifying each training sample. Now the new argument here is the argument gamma. This defines how far the influence of a single training example reaches, with low values meaning far and high values meaning close. This gamma argument can be seen as the inverse of the radius of influence of samples selected by the model as support vectors. So let's start searching for these best values. We can just copy this snippet of the optimization from what we had before. We paste it in here, and now we just need to change this degree to gamma, and we will have two options, the option scale and the option auto. So since this value gamma is the kernel coefficient, if we set this gamma to be scale, then this coefficient is going to be 1 divided by the number of features, multiply with the variance of the data as the value of this gamma, and if we set this to be auto, then it uses 1 divided by the number of features. So we will explore these two options. And then the rest of this snippet is the same, we just need to change the name. So we change this speed to be RBF, this also RBF, here also RBF. Here the kernel is a radial basis function kernel. The maximum number of iterations, let's stay the same, and also the same random state. We perform the exploration, we perform the Bayes search. Remember that all of these arguments were already explained on the previous lesson. Finally, we just change this name to be RBF, like this. So now let's run. This can take some time, some minutes. In our case, it took 5 minutes. We can check what are these best values with the showHTML method. We can just copy the snippet from the previous lesson, we paste it in here. We change the name of the model to be RBF. Very well, here we can see that the best values are the C, this one, 1.51356, more or less, and then the gamma to choose a scale. In fact, we see here that gamma to be scale is the best option in the 5 best cases. Let's now display the classification report of this model using this configuration in here, right, the best estimator that we have found. We can just go again to the snippet of the polynomial kernel from the previous lesson. We paste it in here. Now we just change the name of the model. Now the name of our model is RBF search, and now keep in mind, after doing and performing this search, we have inside this variable, okay, the best model. That is a supervector classifier with the radial basis function kernel with these best values for the arguments. We apply the classification report on the test, right, on the test partition. We are evaluating the performance, so we apply this on the test partition. We run this window, and here we can see the metrics of this supervector machine with this RBF kernel. For the class of astrophysics, we get an F1 score of 90%. Computer science, this here we can compare of the previous one. So here, if we compare the polynomial with this one, we here get more F1 score on the astrophysics class, from 88 to 90. We also get more on the computer science, more in the maths, and on the physics, we also get more. So this is a model that works and is working better to solve this problem. If we compare it also with the linear kernel, we also see that this RBF here is better from this one, which was with linear kernel. The accuracy that we have using the RBF kernel is 0.79, which is the best accuracy so far that we have achieved. Let's now display the confusion matrix using radial basis function kernel. so we can visualize the comparison between the actual and the predicted values. We again just copy the snippet from the previous lesson. We copy here from the polynomial kernel, we paste it in here now, and we just change the name of the model. Now the name of the model here is RBF, Super Vector Classifier, with the exploration of the search. So let's run this window. Right here we can see the results. Remember that the diagonal values are the good values, so we want to maximize these diagonal squares. So let's compare this matrix with the previous one, so we can just copy this and paste it here below. And here we can see from this value, 257 of correct predictions for the astrophysics documents, we have now 264 correct predictions. Of the computer science, we had 219 correct predictions, now we have 228 correct predictions. On the maths, we had 239, now we had 235, so this is decreased. But now on the physics, before we had 214, now we have 218 correct predictions. So overall, this is a better result. As we can see, the radial basis function kernel is the best model so far for the super vector machine on this problem. Now finally, let's plot the ROC curve. This displays the true positive rate against the false positive rate, and this plot leads to another metric, which is this area under the curve. This is a metric that ranges from 0 to 1, and we want this value to be as close to 1 as possible, so we have the best result. To plot this ROC curve, we use the yellow brick library, so we can just go to the snippet from the previous lesson. We create a new figure with pyplot, right in here, and then we use this yellow brick method from the yellow brick library, ROC AUC, and here we can see the ROC curve and also the area under the curve metric. So now the only thing we need to change here is the name of this model, RBF, and now we run. Also, let's change the name of this notebook to be Super Vector Machine with Radial Basis Function Kernel. And now if we analyze the ROC curve for all of the 4 categories, for all of the 4 classes, and we analyze the values of this AUC metric, we can see that on the astrophysics this is the best class, okay, the class where our model predicts the best. We have a AUC of 0.98, then we have computer science with 0.93, maths with 0.93, and physics with 0.88. So now let's compare this ROC curve from the previous one. So here we have these values. If we compare from the previous one, as we can see, when we were using the polynomial kernel, we had a AUC for the maths class of 0.92, and now we have 0.93. So we have increased this AUC value in this model. And the same if we compare it from the linear kernel. The linear kernel has the same AUC values as the polynomial kernel, and so we have increased the AUC value for this maths class using the RBF kernel. So as we can see, the super vector machine with the radial basis function kernel is the best to solve this problem, which is given a document, we need to predict which category this document belongs to. The super vector machine with radial basis function kernel gives us the best predictions results. With this, we finish this lesson. We remind the student that you can download all the code that we have done and all of this notebook on the downloadable documents of this lesson. I hope you have enjoyed the lessons, and with this practice, now you are already prepared to apply super vector machines in Python and understand its evaluation.